Hello everyone. Today class number 44. Class number 44 for electrical machine 2. In this class, I will start the three-phase synchronous motor. Okay, three-phase synchronous motor. So three-phase synchronous motor is most important on the three-phase in synchronous motor is most important part in the winding factor. Okay, so winding. So first topic is winding. How many windings are there? There are three windings. Okay, for three-phase induction synchronous motor there are three windings. First one is stator winding or called armature winding. Okay. That means we know for the advantage to put the armature on the stator and for as rotor, for the rotor case, field winding as the rotor. Okay, so rotor is used as a field winding, or field winding is placed inside the rotor, and armature is used as a stator. Okay, so these are the advantageous structural concept for a three-phase synchronous motor. Okay, and next one, damper winding. Damper winding is an additional winding which used only for the synchronous motor. Okay, so write some point regarding this. So write this point under this section. You have to write one line. So write stator winding is excited by three-phase AC voltage, three-phase balanced AC voltage. That means that it is excited by three-phase AC balanced voltage. Okay, and next write rotor winding or field winding is excited by constant DC voltage, Okay, and the damper winding, right, is a special type of winding. Damper winding is a special type of winding which active only when the speed of the rotor decreases, and which is placed over the surface of the rotor. That means if we want to draw it, that you can see that okay, suppose this is a section of a rotor. It is a complete section and we cut a particular section of the rotor. Okay, over this section these are the damper windings bars. So this is, in this region field winding is placed, and these are the dampers. And this is rotor fringe forging, and this section is pole shoe, and this is a slot. So over the slot is damper windings are installed. Okay, So, and this section is rotor pole core. So these concepts, and this is the damper winding. Okay, so next, right, principle of operation of a three-phase synchronous motor. Principle of operation of a three-phase synchronous motor, right? So point wise, right, you have to point it. So right, a balanced three-phase voltage is applied to the three-phase armature windings. A balanced three-phase voltage is applied to the three-phase armature winding. Okay, so first point, the armature, suppose we are considering okay, this is field winding. Actually, field winding is not the cylindrical. Field winding is salient pole type. So you have to draw a salient pole type. Okay. Field system is a salient pole. Okay. So okay. So a three-phase balance system. Okay, one conductor you have to remove, because actually what happened? Actually, it will connected to it. It will connected to it. Okay, and it will connected to it. Okay, so at a balanced at a stator winding, a three phase balanced winding or three-phase balanced voltage is applied at the stator. Okay, so next point, right, a rotating magnetic field is developed inside the air gap. A rotating magnetic field is developed inside the air gap. And third one, a constant DC is applied. A constant DC is applied on the rotor. Okay, and a constant DC field is introduced to the rotor. Okay, and third point, fifth point, due to the interaction of this air gap rotating field, and a constant DC field, the rotors are excited to rotate. Okay, rotors are continuously to rotate, but at the starting moment, next, right, but at the starting moment there will be a pulsating torque developed inside the rotor. At the starting moment there will be a pulsating torque is developed inside the rotor. Okay, so at that time the damper windings are activated and produces the starting torque to the rotor, and that time the damper windings are activated to produce the starting torque. Okay, so once right, once the rotor rotates, it will continue to rotate by the interaction of the DC constant field to the rotating magnetic field. Okay, so here, and last point, right, it will continue to rotate by the interaction of the rotating magnetic field and the constant DC field. Okay, and last point, right, here in a synchronous motor the rotor will chase, the rotating stator field. Here the rotor of the synchronous motor is chase the rotating magnetic field of the stator, and the stator will drag the rotor, and stator will drag the rotor. Okay, that means it will try to chase it, and the stator field is drags this rotor. That is, there will be a magnetic locking, and there will be a magnetic locking present in between stator to rotor. There will be a magnetic locking present in between stator to rotor. Okay. Next, write. Due to this magnetic locking, the rotor will rotates at a synchronous speed. Due to this magnetic locking, the rotor will rotates at a synchronous speed. Okay. So this is the field winding. This is the operating principle of a three-phase synchronous motor. Okay. So now I will move into the next topic. Right. Most important topic for this synchronous motor concept. Right. Why synchronous motor? Why synchronous motor does not have self-starting property? We know, right? So at the starting moment, damper winding will produce the starting torque, but inherently the rotor cannot move, right? So why? Right. Consider a two-pole salient synchronous motor in which a three-phase voltage is excited. The stator. So a rotating stator field is developed. Okay. The field winding, then write para change. The field winding in the rotor is excited by the DC voltage. The field winding in the rotor is excited by the DC voltage, producing a constant DC field, to rotor. Okay. A constant field to the rotor. That means if we consider it is the south pole and it is the corresponding north pole. Okay. So next, write after that line, write. Let us assume at a particular instant, the upper part of the, please draw it. Okay, first, then you can write. Okay. So at a moment, the upper part of the rotor induced by south pole and the lower part of the rotor is induced by north pole. Okay. But the rotating magnetic field rotates with a speed of ns. Rotating magnetic field rotates a speed of ns through this air gap. Okay. So when the north pole of the rotating magnetic field comes near to the south pole, when the north pole of the rotating magnetic field comes near to the south pole, and simultaneously the south pole is near to the north pole of the rotor, and simultaneously the south pole will come to the near to the north pole, then it will try to rotate in forward direction. Then suppose here the north pole and here the south pole is generated at a particular instant, then the rotor will try to rotate in this direction. Rotor will try to rotate in this forward direction. Okay, whatever the direction I am taking, that's forward direction. Okay. So next, right after the half time period, that is t by 2, that is 1 by 2f second, whatever the frequency of the stator field, suppose it is 50 Hz, that means 1 by the frequency is 50 Hz, that is 1 by 2 into 50, that is 1 by 100 second. 1 by 100 second, that means 0.01 second. So after that duration, after that half time period, that is 1 by 2f second, after the rotating magnetic field polarity changes. The rotating magnetic field polarity changes. That is, a south pole comes near to the south pole of the rotor, and the north pole comes near to the north pole of the rotor. Okay. So at that moment, the forward direction rotation is stops. Forward direction rotation is stops, and at this instant the rotor will try to rotate in backward direction. So rotor will try to rotate in backward direction. So after a particular moment, it will try to rotate in forward direction, and after that 0.01 second, it will try to rotate in backward direction. So there will be a pulsating rotation. There will be, once it is rotating forward direction, then it will be negative, backward direction. Again positive, again negative, positive, negative. So this type of rotation will take place inside the rotor. Okay. So right, due to the high rotor inertia, rotor will not achieve any of the speed produced by the rotating magnetic field. That is, rotor will have a high rotor inertia, high inertia. That's why this, due to the south pole, never it will follow this rotation in this direction, and the just before case, that is whenever it is here north pole and here whenever it is the south pole, the rotor will never achieve the rotation in the forward direction. Okay, so since two opposite polarities produced within a very short duration, at each of the pole of the rotor, so rotor never start alone. That is, rotor of the synchronous motor does not have any self-starting properties. So the damper winding, after right para change, damper winding produces this deficiency, or produces the effect of rotation or starting of the rotation to the rotor by introducing an extra amount of field to the rotor. Okay, so damper winding is used to start the motor, and then when the rotor will decrease its speed, rotor will fall the speed of it from the synchronous speed. Okay, so that means damper winding have two types of activities. First one, to produce the general starting torque, and second one is to increase the speed when it will fall from the synchronous speed. Okay, so this is all about the three-phase synchronous motor introduction. So there will be a lots of topics are there. So next day I will start one by one. So today's class up to this much. Okay, thank you.